Having gone through asynchronous systems, we now go to the other extreme, which are synchronous systems. So what are the model assumptions in a synchronous system? We have synchronous computation, which means that we have an upper bound on how long it takes to perform a computation. We have synchronous communication, which say we have no upper bound on message transmission delays. And also we have synchronous physical clocks, which say that nodes will have physical clocks and there are known bounds on clock drift rate and clock skew. So there are systems designed that can guarantee these properties, in particular embedded systems and systems on chip. We're going to have a discussion about why we study synchronous system. So you can give your opinion, but an important aspect of synchronous system that it is easier to solve problems in the synchronous system model. And we can develop algorithms that tolerate more process failures and develop algorithms that are more resilient to failure. Now we turn our attention to partial synchrony, or partially synchronous system. So what are partially synchronous systems? They are asynchronous systems which eventually become synchronous. You cannot know when, but in every execution, some bounds eventually will hold. It is just a way to formalize the following, that your algorithm will have enough time window where everything behaves nicely, like in a synchronous systems, so that it can achieve its goals. So a question that also could be discussed in the forum is, do these systems exist? Are there such systems? My opinion is that partial synchrony is a theoretical construction when trying to prove correctness property of certain algorithm. It is an approximation of a system that has some periods where the system is stable and some other periods when the system is unstable. So if we look to what I just said, your algorithm will have a long enough time window where things behave nicely so that it achieves its goal. It is actually useful when proving liveness properties of algorithms, as you will see, for example, in proving consensus. So what I just said is that the system will start at a certain point. It is asynchronous, but then at a certain point of time it becomes synchronous. We don't know when that happened, of course, but we will have a period which long enough so that the algorithm can terminate or produce the results that it wants to produce. Notice that the time at which a system behaves synchronously is unknown. So when you design an algorithm in a partially synchronous system, we have these two classes of properties, the safety properties and the liveness property. When you're designing the algorithm to prove the safety property, we need to assume that the system is asynchronous. While when we try to prove that the liveness property, we use the partial synchrony assumptions to achieve, say, the eventuality that something good will happen. The last system that we are going to study is timed asynchronous systems, and this we will study in part 2 of the course. There are no timing assumptions on processes and channels, so the processing time varies arbitrarily. No bounds on transmission, but processes are equipped with a physical clock, and there are bounds on clock drift rate and clock skews. With this assumption, it is possible to design what is called interval clocks. What are interval clocks? It's a clocks at each time t, the clock of a process P is in an interval where the time t occurs. So it will be like this. At time t, there's an interval. Maybe we call it with this row, and that is row. So what we know that the time t is within this interval. And of course, what is exactly rho, this interval, will depend on the process and on the communication network.